Hello, this is Hui Zhao from the University of Cambridge. Today, I'm glad to present our PCB inductor to you. Integrating inductors has been widely applied in semiconductor industrials. The company has devoted great effort on analyzing the patterns and the shapes for integrating inductors. However, these inductors are not suitable for high-power converters because they cannot handle large current. Migrating the technique to PCB can increase the current capacity, but we need to understand which is the optimal structure. Based on the research published by MIT and Stanford, we realized that the square inductor has the maximum inductance. Here is the design of our inductor. The pattern is spiral and its shape is square. Even its size is smaller than a 1-pound coin. Its inductance can be 60 nanohenry and it can tolerate up to 5 amp current. How about if we want to further increase the Q value or the current capacity? We can simply solder several inductors so that they can parallel together. Figure 1 shows that when paralleling inductors together, the equivalent series inductance remains the same because of the mutual inductance. However, the equivalent series resistance decreases fast. Figure 2 shows that even with 5 inductors paralleled, the thickness is still very small. Figure 3 uses simulations to verify that the inductance remains the same and ESR decreases by 5 times when 5 inductors are in parallel. Power inductor requires small resistance, but when the resistance is too small, conventional instruments like impedance analyzer can hardly measure the resistance. From the datasheet, within 10% accuracy range, the minimal resistance can be measured is above 150 milli, and cannot measure our inductor's ESR, which is 35 milli in single piece and 7 milliohm in parallel piece. This is the reason why we use vector network analyzer for the impedance measurements. There are two advantages. First, we have the standardized calibration procedure to calibrate the error introduced by the cable or by the resistance change. Second, we have various configurations as listed below. If the resistance is large, we can choose the second configuration. If the resistance is small, we can choose the third configuration. Here is the measurement setup for the second configuration. Our inductor is connected to the specific standardized kit. This kit has 3 ports. The first port is connected to port 1 to generate the waveforms. Other ports are for the port 2 to measure the waveforms. Port 2 is split into 2 ports to improve the measurement accuracy. One port is to measure the magnitude and the other port is to measure the phase. By this setup, the valid impedance range is within 20 milliohm to 600 kiloohm. Here is the measurement setup for the third configuration. The valid impedance range of this configuration is only 1 milliohm to 100 ohm, and this range is not that commonly used, so the commercialized specific kits are not available. However, we can always build our own kits with standardized components. Here are the details. We have a T-type connector with 3 ports, 1 port to connect our inductor, and the other 2 ports are connected with port 1 and port 2 inside the VNA. Obviously, the impedance of this T-type connector must be calibrated, and here we can use the same T-type connector, the standardized 50 ohm resistor, the standardized 0 impedance for the open calibration, for the 50 ohm calibration, for the short calibration, so that the impedance of this T-type can be calibrated. After fully calibrate the T-type and the cables, our parallel inductors, whose ESR is only 7 milliohm resistance, can be also accurately measured. And here is the photo of our test setup.